Hi guys. So I thought it'd be useful to put together a short video explaining how to take or how to approach this question from the notes on overcurrent protection. So this is a nice question in that it brings everything up from first principles, but it can be a bit overwhelming at the start if you haven't seen it in a while or seen it before. So I thought it'd be useful to go through an example at least once and have a recorded version of it because that can help with your practice for these questions. So this is from the notes and it's problem 2. And it's saying here we have a 400-volt three-phase lift motor supplied from the switchboard by 16 mil squared multi-core PVC SWA PVC cable with copper conductors. So that's given us a bit of a setup for the question. And we're also given a number of parameters here that the cable length is 30 meters, the cross-sectional area of the steel wire arm is 50 mil squared, and we have the K factor for steel, so that's taken from the regs. We've also been given the resistivity of the copper and the resistivity of steel. So this tells us the amount of ohms per meter for this material, and that's per meter squared cross-sectional area as well. We've also been given the earth loop impedance from the switchboard back to the supply transformer, and we're told that this circuit is protected by means of an 80 amp fuse. And we'll tackle the first part of this question in its first video, and it's to evaluate whether the steel wire armor is adequate as a circuit protective conductor. So this is really just checking to see if we have a fault of a certain size, will the steel wire armor be capable of handling the electro energy on this fault? This is something we've talked about before. So I'm going to move over to the overhead camera for this part. So as always with these questions, I always write down on my page what I'm given in the question. And while it's not required and not answered yet, it is always helpful to sketch out a example of the circuit. Now, I'm going to add in a voltage supply here of about 230 volts. That's our single phase. It's a 400 volt three phase supply, but we're looking at one phase. And we've essentially got a cable going to our load, like so. And we'll have some sort of protective casing around this load. And we'll have our neutral going to our load as well. And we have the circuit protective conductor coming from the casing back as well. So just grab another color for that. This is our circuit protective conductor in green. And what we're trying to work out is if there was a fault between the phase and the protective conductor, so we'll say a fault from here to here, that's a fault. Given the conductor that's been used and the circuit protective conductor and the external impedance, is it adequate to use steel of that size? So let's step through that. So in fact, our entire circuit, this doesn't represent it completely, but the entire circuit looks something more like this. We're going to have a 230 volt supply from our transformer, that's one phase. And we're going to have the impedance from our external measurement, that's this value here. Then we also have the resistance of the copper conductor, or Cu, or resistance to copper. And the fault path will be coming back through our steel conductor. So this, in fact, what we're looking at here is more representative of the fault scenario. Now, we are given this value in the question, but unfortunately, we have to calculate the resistance of the steel and copper elements, because we're not given these directly. So we have to calculate these using our resistivity values. So let's get these first. If we want to get the resistance of the copper section, if we go back to our fundamentals for calculating the resistance of a conductor, it's the resistivity multiplied by the length divided by the cross-sectional area. And we have all these values for the copper. Rho for the copper is 17.3 by 10 to the minus 9 ohms per meter, ohm meters. The length of the run is 30 meters, so we can put that in as 30. And the cross-sectional area is 16 mil squared. Now, our conversion from millimeter squared to meter squared, we know that 1 meter squared is about 10 to the power 6 millimeter squared. So if we invert that, we can get that 1 millimeter squared is about 10 to the minus 6 meters squared. Just put that as an aside. So for every millimeter squared, we have 10 to the minus 6 meters squared. And we have 16 millimeters squared here for that conductor. So that ends up becoming 16 by 10 to the minus 6 meters squared in terms of cross-sectional area. So for just to sketch what that is, that's the area of the, if that's our conductor, it's this area in here. And the length then is this here, and rho depends on the material. So that works out at 0.032 ohms. We put that into your calculator. And now at this stage, we have this resistive element. And we can repeat that for the steel as well. So resistance of the steel section, same formula. So it's going to be rho for the steel times the length of the run, it's still 30 meters, divided by the area of the steel, the cross-sectional area. Again, we're given these values, 138 by 10 to the minus 9. We can see then that steel is not considered as good a conductor as copper, but we'll come back to that. The run is still 30 meters. And the cross-sectional area this time, using our conversion, is 50 by 10 to the minus 6 meters squared. We pass it into our calculator. We should get out 0.0828 ohms. Perfect. Now we have this element here. So, we want to work out, is this a suitable circuit protective conductor? We'll go back to the question in part 1. I'm going to mark that this is part 1 here. The next thing we actually need to find out is what is the fault current for this scenario in the case of a short circuit, ISC. Because these are all elements that we have now, we have the external impedance, we have the resistance of the copper conductor and the steel circuit protective conductor, we can just use Ohm's law to work out our fault current. So ISC, that's the short circuit current, will be the phase voltage divided by the total impedance. That's 230 divided by this plus this works out at about 0.6148. And we end up getting 374.1 amps. So that's what we're expecting the fault current to be in this scenario here, where we have a direct fault at that end of our load. Now, our next part of the solution to this question is we need to work out how long it will take our protected device. So don't forget that the circuit is actually protected by a fuse. What's given to you in the question it says here an 80 amp BS88 fuse. So we need to work out how long it takes that fuse to operate for this fault current. So I'm going to move back to the screen for this. Now, this is a little bit grainy, it's hard to see, but these are the characteristics for different protected devices for BS88 fuse. And if you have this in front of you and come to the Adm curve, this is the curve we're looking at here. We go to our fault current here in perspective current, so we've got 374, so that's 100 to about 374. Come up till we hit our Adm curve and come straight across. And it's working out at about 1, 2, 3, 4, about 6 seconds. So I'm just going to take note of that on my page here. The time for that protected device to operate is about 6 seconds. Go back onto the camera. So just so we know where we are, that time to operate is 6 seconds. So with that, we can now use our adiabatic equation and check. So remember, our adiabatic is I squared times T, and that's the let through energy, and that has to be less than or equal to K squared times S squared. So that's the constant for steel, and this is our cross-sectional area in millimeters squared. So rearranging that to get S on its own, because we want to see how does it compare to what we've used. We get that S is equal to the square root of I squared T over K squared. And sorry, that should be an equality here, so less than or equal to. Put in our values. That's 374.1 squared times 6 divided by 51 squared, and we get out 18 millimeters squared. So we're okay in this scenario because we've designed it to have 50 mil squared, but 18 millimeters squared would be appropriate in this scenario. Okay, so that's the first part of that question. I'll just zoom out so you can see the full page before we finish that part. All right, so we'll come back to the further parts of that question in the next video.